right?
Yes, sir, it's visible.
Yes, sir.
Okay. So just yesterday we had our last class, so I believe like uh, you can follow easily. So another thing, just as I mentioned, so let me put on full screen. So so please let me know if I make any mistake. So similarly, so yesterday I made a mistake. So in when writing this current equation, so this E will not be here. Arpit, did you notice this?
No, sir, sorry, I did not notice.
It's fine. So like try to follow again.
Yes, sir.
Uh, so it is simply NQVDA because again VD is actually your new E. Okay. So we cannot write E. So this is so yesterday I made this mistake. So it will be actually NQVDA. So in that case, the area will be unit area. So in that case also, if we just consider 1 ampere of current flowing through our semiconductor, and then we have 10 to the power 18 number of carriers, which have like now the electronic charge is 10 to the power 19. So once again, it will not be here. So for per unit, if you consider this is 1 centimeter square, our unit area, so then also our this drift velocity will be around 10 centimeter per second, something like this. So you can now guess like which is obviously very small than the thermal velocity. So this was the mistake I made, and this is the corrected form. And so finally, we concluded that like on how this different microscopic parameter such as carrier concentration, mobility, or the saturation velocity or the velocity of carriers will decide your overall current density. So again, this is the conductivity of your material. So now, anything else? Okay. So now today we'll go a little deeper, or we'll look into more details of your carriers in transport. So, so see if you think, or if you just follow this classes properly, you will see like initial first I'll try to give some overview, broad overview, then I'll gradually try to dig into more and more details. So now similarly today we'll try to see what are the phenomenon and what are the fact which will essentially decide this VD or VTH, like that means the thermal velocity as well as the drift velocity. So that we'll see in detail. So similarly, like like we have calculated the carrier concentration in detail. Like the carrier concentration, depends on your Fermi-Dirac distribution as well as the density of states. So similarly, we'll try to discuss the detail of the carrier transport. Again, obviously, like this carrier transport, till today, like people are doing PhD on this simple carrier transfer. So there are a lot of detailed things. So of course, like we will not be able to cover all of them, but still we'll look into more details so that we can explain few more characteristics of carrier transport or carry your current in semiconductor. So now carrier transport in semiconductor, if we broadly categorize, we'll see this three types or this four type of carrier transport. So one, this drift. So the carriers having this drift type of carrier like transport, and as well as that there could be diffusion of carriers, which will also give us current. And then this thermoelectric current, this is coming due to the temperature gradient. So this is a, different type of device. Mostly we'll discuss these two current transport mechanism or carrier transport mechanism, that is drift and diffusion. And another type of transport mechanism is tunneling, if you know this term before. So now, once again, so just quickly, if I define with some example. So this drift, you know, that simply if we take a semiconductor bar and then apply some voltage across this, then the carrier will have this drift type of transport and we'll get the current. And now in case of diffusion, what is happening? So diffusion means, once again, let us take a semiconductor bar and now shine one side of this semiconductor bar with the light, where the photon energy is greater than the band gap of your semiconductor. That means H mu is greater than the Eg of your particular semiconductor. So then what will happen in, if we just draw the, let's say this is a p-type semiconductor. So due to this light shining at this edge, so your carrier concentration will be larger in that side, and gradually it will decay. So now you can see there is a concentration gradient with the distance in your device. So accordingly, you will get the diffusion of, like, your carriers will diffuse. So from high carrier concentration to low carrier concentration, and then once again you will get the current, and this current is nothing but the diffusion current. So now another type of current, just to complete this discussion, I am informing you. So let's say we have one semiconductor, then we have one side hot and another side cold, like hot, cold. So then if we connect through a multimeter, so just simply, if we take one multimeter, then if we heat up one probe of this multimeter and keep another probe cold, then we'll observe current in certain direction. So now, so that this direction of current will actually decide whether this is p-type semiconductor or n-type semiconductor. Okay. So this is actually another way to know, because you know, when we are taking certain semiconductor, so we don't know, we may not know like whether this is n-type or p-type. So in that case, whether a particular semiconductor, if I give you and to check whether this is p-type or n-type, you can do this very simple experiment. So this is again nothing but this your thermoelectric current. So now what is the tunneling current? So tunneling current, you can observe, let's say we have two metal plate, and in between these two metal plate we have insulator. So this insulator, let's say this is insulator, let's say. So, and this insulator thickness is some or like some Armstrong, tens of Armstrong, let's say 10 or 20 Armstrong. So this is important in case of tunneling. So now if we apply this voltage, so now if we apply DC voltage, so what will happen? This current can go through this insulator. So this is a metal contact. So this is nothing but this metal. These two sides we have metal, and in between we have insulator. And if we, and now the main parameter to observe this tunneling is the thickness. So it should be of the order of Armstrong, like a few orders of nanometer. So uh, this background noise is am I clear to all of you? Like I do understand like there is some background noise, actually some civil work is being going on. Is this fine for all of you? Like,
Yes,
or
sir.
okay, okay, okay. Actually, this is a new building in our campus, and I'm in new office. So some civil work is going on just in the next office. Okay, let me continue. So now here the main parameter to observe this styling type of current is the thickness of your insulator, and it should be of the order of some Armstrong, like maximum 5 nanometer. Obviously, it depends on lot of the parameters. So now see we are we applied here some DC bias. Here we can observe this current, and that current is due to the tunneling. So another thing, just quickly, if I ask you, have you seen this kind of circuit anywhere else? Like you have metal in between insulator and current is flowing across? Just quickly, have you seen this kind of circuit anywhere? Any quick response?
Capacitance.
Yeah, capacitor, absolutely. So capacitor. So, but here, in case of capacitor, if you know, so they, actually this is the difference. That is why I asked you this question. So in capacitor, obviously there is no limit or as such no limitation on your this, thickness. And the capacitor, this current is, if you can recall that. Maxwell's equation. So there is a displacement current because you know in capacitor only AC current can flow, and AC current is the displacement current, not the conduction current. Okay, so the actual electron will not go from one so actual carriers of the electron will not go through your insulator. So in case of capacitor, I'm discussing. But here, your actual electron will cross this insulator. How it will cross? Obviously, the question is how can this electron can move from one metal contact to another metal contact in case of tunneling? Because again, this tunneling, that is why I kept this tunneling separate from this group. So this tunneling is purely quantum mechanical phenomena using classical concept or classical physics where mainly electrons are treated as a particle. You cannot explain this kind of current. To explain this tunneling current, you need to invoke this quantum mechanics or quantum behavior where electron wave behavior we need to consider. So see, there could be current. So this is the thing. So this is your quantum tunneling. And here electrons are wave, not particle. Okay. And so that means this tunneling is purely quantum mechanical phenomenon where electrons are wave, mechanical phenomenon, this tunneling. And what about these three? So these are called semi-classical transport. These are called semi-classical transport. Yeah. Yeah. Okay. Fine. Semi-classical transport. So why this is called semi-classical transport? Because for simplification, we can consider electron as particle, and when considering electron as particle, we can still invoke this Newtonian physics, and we can explain this carrier transport, this drift, diffusion, and thermoelectric. But still, if we want to understand these three type of carrier transport in detail, like we'll see all of them are like quantum mechanical, it will show the quantum mechanical behavior of your electrons, or electrons can be treated as wave. So if we, but still we can use this classical physics or Newtonian physics where we can consider electron as particle, and we can discuss or we can explain these three type of Fourier transform. But remember, you cannot explain or discuss this tunneling considering this classical Newtonian physics. So that is why this is purely quantum mechanical phenomena, and this is semi-classical phenomena. So not purely quantum mechanical, because we can still discuss using this Newtonian physics. Okay, so these are some basics of these 3 or 4 types of transport. And okay, so here I think the same thing. So result of superposition. Okay, so before we get started, so let us okay, let us see few behavior of carrier transport in semiconductor. So this is electric field versus your saturation velocity or velocity of carrier. So this velocity is that drift velocity. Okay, so this is not that thermal velocity. This is not that random motion. Okay. So now if we observe, so see initially the relation between your velocity and the electric field is linear, and gradually it will get saturated. Okay, so okay, like again, if we quickly recall, I wrote your current as function of number of carriers as well as mobility or saturation velocity or mobility or velocity. So I mentioned this either like mobility or velocity. Now you can see why I mentioned mobility or velocity. Why didn't I mention simply mobility or simply velocity? Because see, when your electric field is small, then only you can see this. It has a linear dependence. Like velocity has linear dependence on electric field, and that constant is nothing but the mobility. So this slope of this curve is the mobility. Now, at high electric field, when your this velocity will get saturated, so that, at that time you cannot use this v equals to mu e formula, because this equation is not valid if you operate your device here, because here it is not linear. Like you can from simply this graph you can understand like the relationship between your velocity and the electric field. If we operate at very high electric field, your silicon device, it is not linear, so you cannot simply use this equation. So that is why I mentioned like either this mobility or the velocity, depending on the bias or the electric field we are applying across the device. So this is the behavior in case of silicon. So this is called saturation velocity. Above this saturation velocity, remember this is intrinsic material property. So if we take silicon, so the carriers in the silicon cannot have higher velocity than this. An exact value, I think, of the order of some 10 to the power 7 centimeter per second. So above this, your velocity will not go. So now you can see like these are the material limit, and again this speed of carrier will decide how fast your device will operate, the frequency at which your device will operate. So now you can see these are the intrinsic material property, and you cannot use if your requirement is something higher than this velocity. So these are material property. Now, in case so this is the behavior, this is the same characteristics between your saturation velocity and the electric field, but this is in case of gallium arsenide. So here, this is some interesting behavior. Again, to discuss this, you need to take help of your band structure. That is why I told you, like if you know this band structure very well, you'll be able to explain a lot of other phenomena or a lot of other observation of particular material. So here, initially the electric this velocity will increase, then it will decrease. So here it shows some negative differential this resistance. So using this again, I think people have developed some other microwave devices, some oscillator type of devices. So whenever there is this negative, so here if you take del V del E. Again, essentially, this is your current and versus, and this is electric field, nothing, again, your voltage. So this is some resistance. So this negative, this is some negative differential resistance. And this negative differential resistance people have used to fabricate this some microwave devices. And it can be only used, you can see this behavior is particular to this gallium arsenide material. So these are the observation, and obviously we'll need to explain from microscopic point of view why this observation, why this carrier velocity is getting saturated, and why initially it is increasing linearly. So all these phenomena we need to discuss. Okay, so this is again some the same characteristics, but with some value. So again, yeah, so I think for silicon it is of the order of 10 to the power 7, and then this is the gallium arsenide. So okay, so this is another characteristics. So this characteristics is your mobility. So that once again, just consider this knowledge. We'll obviously see what are the other phenomena which is running behind this equation and all. So if we consider this V equals to mu E, so this mobility we know, and this is the behavior of this mobility with the temperature T. So if we look at, so first let us discuss these characteristics. So here we have doped our semiconductor with the 10 to the power 14 doping level. So that means the impurity or dopant atom is 10 to the power 14. Okay, so now you can guess like this is silicon. So in case of silicon, 10 to the power 14 means 10 to the power 22. So that means 6, 8. So out of 10 to the power 8, for each 10 to the power 8 number of atoms, you will find one atom dopant atom. Okay, so that means this is actually very low doping level, doping concentration. So at this doping level, if we increase the temperature of that particular semiconductor, the doped semiconductor with the 10 to the power 14 dopant, so we'll see whenever we'll increase the temperature, the mobility will decrease. So what is the problem if mobility decreases? Obviously, you will get the lesser current and all other effect will be able to observe, because mobility which will decide current as well as the frequency also. Frequency of the operating, operating frequency of your device. So now you can see with the temperature, this mobility is decreasing. That means at higher temperature, if you operate, so that means you will get lower current from your device. So now this is when you have doped your semiconductor 10 to the power 14 dopant. Now if we increase the doping level from 10 to the power 14 to 10 to the power 16, 17, 18, again 10 to the power 19. So if this is very highly doped semiconductor. Now in case of highly doped semiconductor, see at very high temperature, the mobility is decreasing. But when we dope this semiconductor very highly, at low temperature also this is decreasing. See, but earlier this was not the case when our doping level was low. So that means there is something happening when we doped our semiconductor high, isn't it? So this is we are increasing the doping level, and the mobility at low temperature also decreasing. So mobility at low temperature also decreasing, mobility at high temperature is also decreasing. Now obviously the question is why? So that we need to explain. So this is another behavior where it is showing like the mobility with the impurity concentration. So whenever your impurity means doping. So whenever you will take semiconductor with high highly doped semiconductor, so your the mobility will decrease. So this is in case of electron, and this is in case of hole. So this hole and electron mobility is obviously, you know, that is typically lower, like hole mobility is lower than the electron mobility. And similarly, this is in case of silicon, this is in case of gallium arsenide. So the overall observation from these two figures are see that if we increase the doping level, the mobility will decrease. So just think to get your high current, so we can either increase the number of carriers and this your number of carriers. We can either increase the number of carriers, but see now, if we increase the number of carriers, or if we dope our semiconductor highly, our mobility is now decreasing. So now you don't know whether by increasing this carrier concentration, uh, overall you will get higher current or not. Because if we increase the carrier concentration, your mobility may degrade. So then you may not get higher current. After, obviously there is some trade-off. Okay, so that why this is happening, this also we need to discuss. So this is once again this resistivity versus impurity. So it is almost like same. Now resistivity means, this is again conductivity you can consider. So here you have both this carrier concentration as well as the mobility. So here also you can see this resistivity is decreasing overall. That means conductivity will increase. Okay. So these are some characteristics of behavior. These are all experimentally observed characteristics. Now let us explain all this. So to explain all these characteristics, we need some background, and that background already we have discussed some part of this background. So the thing that we need to know, that is random thermal motion. So this random thermal motion, random thermal. So this random thermal motion we have already discussed in previous classes. So whenever we'll keep our semiconductor at certain temperature without giving any other energy, so then the carriers will have this motion, and this is like purely random. So here we know that your after generation of your particularly electrons, so it will take some random path before it recombine with the another hole. So this is obviously at T0, T greater than 0 Kelvin, and the few other properties it has. So that we'll discuss here. So first is, so there are a lot of scattering. So after generation at this point, so these electrons will get scattered here, here, and here. So remember this word scattering, okay, because there are few other terminology like reflection or some other terminology we will not use. Why we will not use that also I'll mention. So these are all scattering. So what are the different type of scattering involved? That will actually decide what will be your mobility behavior in the semiconductor, with temperature variation, with carrier concentration variation, with other parameters also. Mainly this scattering is the fundamental phenomena which will decide the behavior of carriers under when it is having some transport. So this scattering, so typically there are three types of scattering. Again, scattering means it will collide with some particle, with some atoms, because in crystal you what are the element these electrons will find? Either atom or this ion, because why this ion? Because if we dope your semiconductor, after donating one electron or hole, that particular atom will be ionized. So then that means, so after generating electron here, it is getting scattered at this point. So at this point there might be some other electron, might be some other hole, might be some other neutral atom, or might be some other ionized atom. Okay, so these are the 3 or 4 entity you can consider here that causes you that causes this electrons getting scattered in another direction. So what are the scattering this phenomena? So one is, so first one is called phonon. Second one is electron or hole. And the third one is impurity. And mostly ionized impurity. Ionized means this after donating one electron or accepting one electron, that particular atom will be ionized. So now what is phonon? Phonon is nothing but the vibrating atoms. This phonon is the vibrating atom. So why this phonon is coming and why these atoms are vibrating? You know this, whenever we heat up our sample, so so you know that this all the atoms are properly arranged in a crystal form, and in a particular semiconductor. Now if we heat up the semiconductor, what will happen? So the atoms will vibrate. So atom will start to vibrate, and that vibrating atoms can be the cause of your this scattering. So when you know this, if I, so that lattice, you know, these atoms are here. Now these are all bonded. Now these atoms will vibrate. So this it will vibrate. So the more will be the heat, the vibration will be larger. So that vibrating atoms may lead to this scattering of your electrons. So that is called phonon scattering. This is also called lattice scattering, because this is also called lattice, atoms bonded with the another atom. So this is also called lattice scattering. So another now this electron hole. So here you can this is typically called carrier scattering, because electron when it will see another electron or another hole, so it will get scattered. So this the name of this type of scattering is called carrier scattering. Now this third type of scattering is called ionized impurity scattering, simply with the name. This is a impurity, this is ionized. So this is ionized impurity scattering. Now see this scattering, this first type of scattering, this phonon scattering is also physical scattering. Why this is physical scattering? That means this atoms are vibrating, and then electrons, it will directly go and may collide with this and get scattered. So this is physical scattering. There is physical collision. But what about this next two? This carrier scattering, as well as this ionized impurity scattering, these two are called action at a distance. Action at a distance. Why it has this name? Is so that means is so this is not just physical scattering. So is this mean that electron will not go and collide with this another electron on the hole? So what is this action at a distance? So the action at a distance is, let's say we have one electron, let's say, and then we have, let's say, this ionized one acceptor ion, which is again this negatively charged. So when this electron will come and see this, it will just go in this way, because it will repel it back, or this electron will get repel back to this direction or any other direction. So this, because this is a negative. So that is why this is not physical scattering. See, this is charge-based event. It has electronic charge. This electron has negative. This acceptor ion. This is also negative. So it is electronic. This repulsion is there, and this kind of scattering is there. So that is called. This is action at a distance. So similarly, if here now you have another electron. Similarly, this similarly this will get scattered like. So similar kind of repulsion will be there. Now what will be in case of we have hole, because that is positively charged. So now if we draw quickly here and let's say hole here. So what will happen here if we have positive hole and negative electron? So it will come and will get attracted. So but it will take this kind of path. See, it was going like this. So now due to this positively charged hole, now it will get deflected. So its path is getting deflected and it is getting scattered. So once again, this is scattering due to hole. So now next question, obvious question you should ask me, so whether there will be recombination, because this is electron negatively charged, this is hole positively charged. So why can't it go just simply and go and sit there? What is the problem? Then there will be recombination. And what is the probability that it will get deflected or it will get recombined? So the probability, if I say the probability of this getting deflected is more than the recombination. Now, why this is the fact? So the thing is, there are a lot of other energy related favorable condition you need to have, because whenever you can understand like this electron is having some kinetic energy, so then whenever it will get recombined, so that this energy, that kinetic energy will need to transfer to another type of energy. So all other things are there, but most likely whenever this electron will see another hole, positively charged this hole, so it will get deflected. Okay, again so like for all the case, like whether electron hole, electron acceptor ion, or electron, so all these events actually they are action at a distance. They are not physical scattering like your phonon or where you are having vibrating atoms. So that is why this is called action at a distance. So if we have any doubt, please stop me and let me know if you have any question. So now, okay. So scattering again, that there is also something called reflection. So this here, you have this kind of this change of direction in carrier path. Is this scattering or is this reflection? And when you will call it reflection, and when you will call it scattering? So because there is a difference between scattering and reflection. So because scattering, whenever you will have scattering, the direction cannot be predicted in case of scattering. But you know that in case of reflection, the direction can be predicted. So this is the difference between your reflection and scattering, and that is why when using this terminology, that we should be very careful. So these are all scattering; these are not reflection. Okay. So now there are a few more things. Okay, I can use this picture. So there are a few more concept called mean free path that you have already I think understood in the last few classes. So mean free path is the mean path between these two collision, and then this is typically LC. The mean free path is LC, and then we also have the concept of this mean free time. That means the time mean time between these two collision, that is called tau c. And now this another term, that this is called thermal velocity. So this is again random. Whatever we are discussing till now, all this random motion. Okay, there is no current. So this motion is coming purely due to the thermal energy. Now, once again that in the previous class we saw or we calculated that this random velocity. Okay, now if we just write this thermal velocity, it is also equivalent to your LC divided by tau c. Okay, so this is the mean free path divided by mean free time, and it will give us the thermal velocity. So this thermal velocity is very high. So this is also called sometime intense motion. This is also called intense motion. So if I write, I think now I need to change slide. So the observation that we concluded or we have seen this, there is a huge intense motion, but no net motion. So it has very high thermal velocity, but there is no net motion, there is no net current. So there are few properties, like if we summarize now these properties of random thermal motion, it is called random thermal motion. So okay, so there is no net motion. So why I am writing this word and this thing like multiple times, it has the reason, because using this concept, actually whatever we are discussing now, we'll see how we can explain those three semi-classical transport. That means how with this concept the current, that means your drift current, diffusion current, as well as thermoelectric current can be related. So that we will see. So now in case of this random thermal motion, we know that there is no net motion. So how can we interpret this? There is no net motion. So there are several ways that we can interpret this. So okay, I'll just otherwise just I can mention one. This is called ensemble average. So the ensemble average of your like ensemble average of uh, particle velocity will be 0. So what is this ensemble average? So the ensemble average is, if we consider is let's say a small portion of your semiconductor. So again, we know that there are different particles having different velocity to different direction, because these are all random motion. Let's say V1, this electron has a V1 motion, then another electron or the carriers has a V2 motion, and then another carrier may have V3. Similarly, another carrier can have V4. So the ensemble average says, if we take this sum of this all velocity, so at any instant it will be 0. So at any instant, if we observe the velocity of this of all the individual carriers, at any instant, we should mention, at any instant it will be 0. So that means there is no net motion. So this is how we are interpreting this no net motion. And another way we can interpret this phenomena, that is there is no net motion. So it is considering once again a semiconductor And if we consider a plane within a semiconductor, so now there, if we, this is also called a plane of observation. So if we see the movement of all charges or carriers across this plane, so this is a plane, okay. So this is a plane vertical to this sheet of or this skin of your on your laptop or mobile screen. So if we try to see or observe the motion of carriers across this plane, so let me just draw. See, there are two carriers moving from this region 1. Let's say this is region 1. This is region 2. So these carriers are two carriers. Just assume going from this left to right, and then few carriers at the same time will go from right to left. So now if we see the average flux means the carrier per unit time. So across the carriers moving across the crossing this plane of observation, this is called plane of observation. So if we see this average flux or calculate the average flux crossing this plane of observation for some duration of time, it will also be 0. So average flux will be 0. So this is the same concept, the no net motion. So it can be interpreted in this way also. So this is the second way to interpret this no net motion concept. And this concept actually we can take to understand or to explain this drift diffusion carrier transport. Okay, so how to, let me once again redraw this image. Okay, before going to next, this another thing, just so how many collisions are there, like or how many scatterings are occurring there within the semiconductor at obviously at some temperature, because this all random motion, the source or the energy of this random motion is the thermal energy. So at which temperature we are keeping our semiconductor, that will decide, of course, the how many scattering will happen. So if we quickly just see once again, so feed thermal velocity, just to remove. So this velocity we have calculated previously that it is of the order of 10 to the power 7 centimeter per second. This is the thermal velocity, random. And the LC, that means the mean free path, typically, again, all this figure at 300 Kelvin. So if we remember, or if we go back to previous few slide or this last class, we actually calculated this value also. Like if we remember 10 to the power 5 meter per second, we came to this figure after calculating from that 3 kT by 2 and equating to kinetic energy. So anyway, so now this LC, the mean free time is of the order of 10 to the power minus 5 centimeter, obviously. So this is the distance between two collisions. So now if we see these two figure, so what will be the tau c? That means the mean free time. So the mean free time will be, you can easily guess, it will be of the order of 10 to the power minus 12. So obviously this is second. So you can now just why I mention all these digits here, just to give you some feeling, like whenever you'll see all these digits, you'll understand what is exactly happening here, like what is the dimension and what is happening. Like similarly, see, this is the mean free time. Mean free time means the time your carrier will take between two collision. So at the same time, so this is a second, picosecond, 1 picosecond or 10 to the power minus 12 second. So from this particular figure, you can also understand that there are 10 to the power 12 number of scattering happening per second within the semiconductor. Once again, I am repeating this fact. So since your this mean free time is 1 picosecond, so at the same time you can also conclude that there are 10 to the power 12 number of scattering occurring within your semiconductor per second. So these are the scattering per second happening within your semiconductor at this room temperature of 300 Kelvin. So a huge number of scattering is going on, like, okay. Okay, now let us consider once again this concept of plane, this no net motion, and let us discuss this three type of transport. So let me draw a larger figure. So once again, so here I'm considering a uniformly doped p-type semiconductor, uniform p-type doping, and this is the plane of observation. And now I'm observing carrier movement within LC. So this is LC from the plane of observation towards this left side, and this is LC towards right side. Why I have considered LC from your plane of observation? Because this maximum, if we consider one electron hole pair generated at this plane of observation, so it can reach to this LC. After that, it will have collision, or it will get scattered by some carriers or by some lattice or ionized impurity. So maximum it can travel this distance of LC. So that is why now I am considering this LC from this plane of observation towards right side as well as towards left side. And once again, we can give it a name 1 or 2, section 1, section 2, and this is plane of observation. And now, what is the flux? What is the flux which is going from, let's say, this section 1 to section 2, crossing this plane of observation? That means the flux, I'll just take the absolute mod value. So the flux going from this right side, so this left to right. So how many carriers or what will be the flux? Because from the this no net motion concept, we understood that the flux crossing this plane of observation will be 0. So under equilibrium, so again this is under equilibrium condition, because here we are having semiconductor only at certain temperature. There is no other energy or external energy perturbation. So under equilibrium, your flux cross from left to right or from 1 to 2 is, it is p-type semiconductor, and then not only p-type, it is uniformly doped p-type. So p number of carriers per centimeter cube. Okay, so p is the density, doping density. So there are p here also you have p number of carrier per unit volume. So now p multiplied by this volume. What is the volume? So your volume will be, this is LC, and this cross section we are considering 1, this cross section, because see here our objective is to calculate total carrier. So density into LC into 1 is the area, cross sectional area, which is below this plane maybe. Okay, that we are considering 1, like 1 centimeter square. So then this is the total number of carriers which will cross from 1 to 2 due to the thermal energy, and divided by, this is flux. That means the total number of carriers crossing per unit time. So what is the now we need to do? So this is a tau c, because this is the mean period time. So per unit time, how many carriers will cross this from 1 to 2? This is the number. This will be the flux. But still, this is not the final figure. So we need to include one more factor here. What is that? 2. We need to divide this quantity with 2. Obviously, now why we need to divide this parameter with the 2? We need to divide this using this 2 because see, we are considering only this flux or these carriers coming from this 1 to 2, and at the same time we are calculating this flux in case of equilibrium. So that means we also need to consider that there will be some carriers or equal number of carriers that will go from right to left. Otherwise, what will happen? If we just simply consider this PLC divided by tau c, only we are considering this one directed like single this directed carriers. So, but in that case, what will happen? So, like you will have net current. That situation will not be under equilibrium. When it is under equilibrium, so the movement of carriers, like equal number of carriers, will go from left to right and right to left. So that is why only this half of this total carrier will go from this region 1 to region 2, and another half will go from this another direction. Then only you will be able to maintain this equilibrium. Otherwise, there will be directed motion of carrier, and that will give you non-equilibrium condition. So that is why we need to divide this using 2. Now further, if we simplify, this is the number of this is the carrier density or hole density, and this is the LC by tau c, which is nothing but the velocity. So PV by 2, and this is the flux. And under equilibrium, this flux, that means the flux coming from this left to right or region 1 to 2 will be equal to the flux going from region 2 to 1. So that means this is also equal to the flux going from 2 to 1. We can write this also like 1 to 2, and this is like here. I think we should not write like this. Anyway, so this is the opposite flux. So this is under equilibrium. So under equilibrium, when there is no net motion, we have this both flux crossing this plane of observation equal. Now, when we have this equilibrium, that is like this velocity is also called thermal velocity, VTH, we can say.
Sir,
Now,
we have class now.
yes.
Sir, we have class now, like next class.
Okay, so because I want to complete this discussion, so those who have class, you can join this class or you can stay here. So I'll upload this video. Okay, you can check this video. I'll upload just after this class. Okay, because I need to complete this discussion. Okay, so those who have class, you can leave and you can check the video uploaded in the Moodle. Okay. Okay, thank you. So let us continue. So now what is happening under non-equilibrium condition, or when we are having this net current? So first situation we can consider when we'll have some net flux. So this is all equal. Net flux means there will be like one from flux from 1 to 2, another flux from 2 to 1. Now if we want to have some net flux, what can happen? So either we can have difference in the P1 and P2 divided by 2. This is when this is not equal to 0 for P1 not equals to P2. What is this type of transport? Like, see, to have now current, through your semiconductor, we need some net flux. This two flux will be equal when it is under equilibrium, and under equilibrium you will not get any current. Now when you need to have current under non-equilibrium condition, let's say you have applied electric field or you have some diffusion, so then you will have some net motion. So what is that situation? So that situation will be, there will be some net motion of charge, and that net motion can like we can get this net motion when there is a difference between P1 and P2. P1 and P2 is means there is a difference in carrier concentration in region 1 and region 2, which is nothing but the diffusion. Okay, so in case of diffusion, you will arrive to this condition where you will have net motion. Next, you will also get this F net when you will have variation in the velocity. So then it will also be not equals to 0 for V1 not equals to V2. And when you will get this situation, obviously, so this situation will arrive when you are, so this difference will arrive, like the velocity of carriers in the region 1 and the velocity of carriers in the region 2 will be different when there is electric field. And that means this is a drift current. And similarly, this situation will also arrive when you have a temperature gradient, because you know, like let's say here in this region we have the carrier temperature T1, and here we have carrier temperature T2, and if temperature T2 is greater than T1, what will happen? The kinetic energy of or the velocity of the carriers here will be more than these carriers in the region 1. So that then also will get the current, and that current is also your thermoelectric current. So now I think you should have clear idea how this plane of observation concept can be used to explain this different type of semi-classical transport. Again, this drift, diffusion, thermoelectric, these are all semi-classical transport. Okay, so here actually we are having this current as a result of superimposition of directed motion over the random motion. This particular fact I should mention. Superimposition of directed component or directed motion over random motion. So I am telling once again, like, see how there is a random motion, but those random component are having this directed component now. Okay, so how many? Just so how many students are still here? Okay, still 23 students are here. Okay, I'll continue. So just last this comment. So how we can interpret this? What? So this direct superimposition of directed motion over random motion. What is this? Let us take let us take an analogy. So this analogy again is very close to my heart, like you can see. See, let us consider just analogy. This is just to understand this phenomenon, how this directed motion we are getting over the random motion, and still we can explain this drift and diffusion of carriers. So let us consider in a typical, like let us consider a situation in a sweetmeat in a sweetmeat shop, like in a sweet where we purchase sweet. So then let us consider that you might have observed that there are a lot of trays having sweets. So inside a let's say glass cabinet or something like that. So now if we note or if we see carefully, there might be some insects or flies hovering over some sweet tray. So let us consider, let's say we have one sweet tray here. So this is inside a glass cabinet, and we have some sweets here, let's say. And some flies are like hovering around over this this tray. Now, if we gradually just drag this sweet tray from in this direction, what will happen? So what will happen to this motion of insect or motion of flies? So these flies will have some random motion, but this random motion of flies or insects will get some directed component. So they will have this randomness in their motion, but they overall these flies will just shift towards this direction, because we have just gradually shifting this sweet box. So then flies or insect will also shift when just having this random motion. So this is nothing but the same thing is happening in case of drift motion. So now with the same example, we can explain this diffusion carrier transport. How can we explain this? Let us once again consider another this sweet tray. So where we have these sweets. So now once again these flies or insects are hovering over this this tray. Now let us keep another fresh sweet tray here. So just you prepared on another tray of sweets, and you kept it just next to this tray. So what will happen? So they will now move some of the flies or this will just move over this next fresh sweets. So they will have this random motion, but still some of these flies will move from this first tray to this second tray. So this is nothing but the diffusion. So this analogy, from this analogy, now I think it should be clear to all of you that how the two components are involved when we are getting current out of our devices. Because in electronic device, it is all about current when we apply some voltage. So these are the thing happening. Like there are random motion. Then after applying this electric field or creating this gradient of charges, we can get the current or directed component we can. So that is why this is superimposition of directed component over this random component. Okay, is this clear to all of you? Okay. Okay, are you all there? So I'll stop here. How many students? Still 23 students are here. So Any doubts from today's class? Okay, I'll stop here. I'll not go further today. So, any doubts? I'm stopping the recording now. Okay, thank you. If you have doubts, I'll be very happy to discuss. Sir, please tell. Can you, sir, please, can you, what is Deepak Kumar? Please, can you tell me that, yes, so I'll mail all of you. So next Friday we'll have, you know that will not have quiz 1, quiz 2. So we'll have this module 1 test. So next Friday we'll have module 1 test. Okay, so you can inform other your batchmates. So next Friday we'll have this test. So it will be very short test on your module 1. So module 1, I thought I'll be able to complete today. Anyway, so next day I'll complete. So then on Friday we'll have this module 1 test, and it will be mostly like 15 to 20 minutes uh, short test. Okay, so any more doubt, Deepak? Is this fine?
Thank you, sir.
Okay, okay. Okay, thank you everyone. So if you don't have any further doubts, okay, so then we'll once again meet on Tuesday. Thank you.